Hello, right, so welcome to the session. We're going to be covering transition metal chemistry today. So hopefully that image there means something to you. I'm just going to give some credit to Knock Hardy Publishing, which you can actually get online. There's some really good PowerPoints on there. I've taken some of the slides. I've taken out what you need to know for your WJC, but if you want a bit more background chemistry to transition metals, they're certainly there. So it's Knock Hardy Publishing. So this is a carbon chemistry session, and as I say, we're looking at the transition metals. So when I think of transition metals, obviously I think of this block here in the periodic table, the blue block. But actually, some of them are actually classed as transition metals. I mean, it does depend who you're talking to. So, as I say, we're going to look at the 3D transition metals, which is this block here, runs from scandium to zinc. All right. So, what makes something a transition metal? Is it being in the D block? Not necessarily. It's to do with your electron configurations, and particularly it's the ions that you form. So if you're a transition metal, you need to form a stable ion that has an incomplete d orbital, and we're going to look at that with scandium and zinc in a moment in particular. Okay. So they have typical metallic properties, as you'd expect, good conductors of electricity. They've got more the properties of metal that you associate with metals than group 1. They've got much higher melting points, boiling points, densities, and it's because of the size of these ions. As you go across the periodic table, hopefully your ions are getting smaller, and and also the charges that you form on the ions as well is greater. So they tend to be stronger as well. Okay, so typical properties, like I say, of a metal. So what makes something a transition metal then? Well, we'll look at the configurations first of all. We'll focus on copper and chromium in particular. So we've got potassium here, and as hopefully you know, potassium would be an S block element, with its electron being in the highest energy level being an s orbital. So we've got the s orbital being filled here, and then if we go to calcium, we've got our 4s2. All right. Now our next electron, we're going to go into our scandium, and we can see scandium, which has got its 21 electrons. We can see that this electron now enters the 3d orbital. So it's this kind of awkwardness really with the orbitals, and I'm not going to spend too long on this. It's year 12 chemistry, but as you should know, that when we're putting electrons in, the 4s orbital is lower in energy than the 3d orbital. So as long as you remember to put your electrons in the 4s orbital, then start filling your 3d orbital, you should be good. And we start filling those electrons in. Okay, so we're trying to keep the electrons separate from each other. We don't want to pair them up unless we have to. Okay, and you can see here we've got vanadium, and then suddenly we go from vanadium with its 23 electrons, we come to chromium with its 24, and hopefully you recognise that's a bit unusual. Vanadium, the extra electron, you'd expect to be another electron in this orbital here, but we actually see all the orbitals are full. So where's this other electron come from? It's come from our 4s orbital here. So this is you give a more stable atom by having your d shell either full or half full. So please do remember chromium. Of course, examiners quite often ask for chromium because it's the one that catches people out. Okay, after chromium, things go back to normal. We've got our manganese. And then we've got our iron, cobalt, nickel, and now we come to copper. So you'd think now we're going to put an electron in here, okay, which we will do, but also going to promote an electron from this 4s orbital. And in doing so, again, we've got a full d orbital. So the big ones are your copper and your chromium. They have a 4s1, not a 4s2. So please remember that. Okay, and then we finish off with zinc, and you can see here it's now got its full d block or d orbital. Okay, so those are your configurations. Now you'll notice when I write my configurations, even though I do I'm aware of the 4s orbital filling before the d orbitals, I write them in this order. You don't have to. You could put the 4s before the 3d, but it's going to actually help you if you don't. So yeah, try and keep your energy levels together. So you got your 1s, then you got your 2s and your 2p, and you can see I've got my 3s, my 3p, and my 3d. And I've highlighted the copper and chromium for you in red because of their unusual feature of promoting an electron. To get the D block either half full for chromium or completely full for copper. So what do you need to know for the exam? Well, you need to know that the common oxidation states, and there is this little table here, which is it's quite useful for remembering the oxidation states that these transition metals can form. With manganese being the one with the highest oxidation state, and then you can kind of form this pattern with the elements. So you've got the elements running from scandium to zinc. Remembering manganese goes up to +7, and you can just do this kind of pyramid of numbers. However, is it useful? Well, yes, but for the exam, what I would say is it's probably better just to learn that there. Okay, so these are the oxidation states you need to know. And while we're here, I'm just going to point out to you that this is an image that I've taken directly from the blended learning on the WJC. So really very good resource, and I highly recommend looking through that. It does give you, it's quite brief, but it gives you that essential kind of background knowledge. So I'm going to talk to you now about why I write my orbitals the way I do, why I don't put the 4s before the 3d, so why the 4s is coming after. And the reason for that is it's for when you're forming your transition metal ions. What you should know is that the electron, although it goes into the 4s before the 3d, suggesting the 4s is lower in energy, we take the electron from the 4s orbital. So when you've written your configuration out for copper, if we were to write copper plus or copper 2 plus, we're going to take the electron from here. All right, so always remember your ions take your electrons initially from the 4s orbital. Any subsequent electrons to give the positive charge would come from your 3d orbital. So I'm just going to have a little pause, because if you play the PowerPoint back, you'll be able to just check on yourself. And what would the copper plus and copper 2 plus configurations be? So this is going to have an electron taken away, and this is going to have 2 electrons taken away. So you can see there, I've taken my first electron, or my only electron, away from this orbital, and then for the copper 2 plus, taking this electron away and a subsequent electron away from the 3d10. Have a look at the titanium. I'll give a little pause again for you to just reflect. So we're moving 2, 3 and 4. These are reflecting the stable oxidation states. If you look at your titanium, it doesn't form a +1 oxidation state. So look, go. So you can see taking 2 electrons off to move with 3d2, so that's gone. If I want to take 3 off, now I'd start using it, moving into my D block, and then finally, Ti4 plus, you can actually go down to your P block. Okay, and Ti has a 4 plus charge. So the next thing I wanted to do with you was just to talk about your oxidation states, which is year 12 work, but also it's something that's obviously crucial to year 13. And I've got some transition metals here, and I thought, well, this one should be fairly easy for you, copper chloride. Okay, and if we work out oxidation state, we can see we've got 4 chlorines, associate that with a -1 charge. So that gives me -4, and I want to retain a -2 charge, so the copper would be in its +2 oxidation state. This is the tricky one, and the reason I've done this one is I noticed my year 13s, they struggled with this year when we were doing oxidation numbers with redox. And I asked them to work out the oxidation state of the nitrogen and the chromium. The mistake they made was trying to do it from this formula. It's quite difficult to do. So what I suggested they do is to be conscious of these ions. You should hopefully look at that formula, but actually this is ammonium dichromate, and it contains 2 ions. There we are. So it's made up of the ammonium ion, the dichromate ion, and now you can look at your oxidation numbers. It makes life so much easier to do that. So your nitrogen would be so 4 times +1 is +4, retaining the plus charge. This nitrogen is -3. And more importantly for us, for the dichromate, 7 times -2. Oxidation state of oxygen is -2. 7 times -2 is -14. Retain a -2 charge. The chromium must come out as +12, being shared by 2 of them. So now you can see chromium is in the +6 oxidation state. So that's my advice for you. If you've got something that's composed of ions, split it up into its ions. It's going to make your life a lot easier. Okay. So we're going to come back to scandium. Is it a transition metal? Well, it's in the D block, so some people would argue it is, but to be a transition metal, you must form a stable ion, which we've just looked at, the common stable ions, and that stable ion must have a partially filled d orbital. So let's consider the scandium as a transition metal then. So this is its configuration. You'll have to excuse me. I know I've done it the right way. I've got my 3D orbitals all together. That's its configuration. It's got 21 electrons, and it only has one stable configuration, which is the 3+ ion. So if I was to write the electrical configuration of the ion, you can see I'm going to take my 3 electrons away, and now we can see that we don't have a partially filled d orbital. So really, scandium is not classed as a transition metal, even though it's a D block element. And it's the same for zinc, and hopefully you can see why. Here's zinc, and you can see with the zinc, zinc only has one stable ion, which is the zinc 2+ ion. So you can see here, if I take those 2 electrons away to form the 2+ ion, we have a completely filled d orbital. So they're not really classed as transition metals. So, most important thing then, to be a transition metal, you need to form a ion with a partially filled d orbital. So, hopefully one of the things you know about your transition metals is a key property of a transition metal, key feature is they form coloured compounds. And we're going to be looking at where these colours originate from. They also form complex ions, and so we're going to look at the chemistry of the transition metals now in terms of the complex ions. So here's a complex ion. You can see this is for ion 2. The oxidation state here is referring to, or the charge here is referring to charge in the ion. As you know, water is a neutral molecule, all right, so it's not going to bring any charge in, so we can attribute this charge solely to the Fe. So this is Fe2+. And if we dissolve it in water, say we had some iron chloride and we dissolved it in water, this is what we would form. We'd form this complex ion. What's a complex ion then? Well, your exam board really do like you to be able to describe things. You know, they may ask you what is a complex ion. So you can see here, you've got a central metal cation. It doesn't have to be a transition metal to be a complex ion, but typically transition metal ions do form them. And we've got these water molecules surrounding the central cation. These water molecules, hopefully you'll be familiar with the term, these are what we call ligands. And they have joined onto the water. They are actually covalently bonded to the ion using what's called a dative bond. All right, and we'll discuss that as well because it's year 12 chemistry. You may have forgotten that term. Just talking to you then why the transition metal ions can actually form these complex ions. It's to do with the energy levels being so close together when we get to this point. Okay, so you know, as you know, your 4s and 3d are very, very close in energy, and your 4p is pretty close as well. So it's actually the reason that transition metal ions can form these complexes is they have what are called vacant orbitals, and it's these vacant orbitals that the water molecule forms its dative bonds to. Now, don't worry about this picture here. You don't need to know about, you know, the 4s and 4p and 4d orbitals being involved. You just need to know that it is vacant orbitals which the ligands kind of dative bond to. This is why transition metals can form these complexes. These are not vacant orbitals. All right, they have electrons in, so you couldn't dative bond in here, but you can with these orbitals. Okay, so we're going to look at some ligands. Like I say, ligands form dative bonds to the central transition metal ion. So obviously, the thing that you're going to need for a ligand is to have lone pairs. So what's a dative bond then? Well, it's a covalent bond in which both bond pair electrons come from one atom. Like I say, that's your 12 chemistry, but you could be asked to define what a dative or coordinate bond is. Sometimes they're called dative, but I think on your syllabus they are called coordinate. So, like I say, you've got to have lone pairs. These are what are going to bond into the vacant orbitals on the metal. So typical ligands are your chloride ion, your hydroxide ions, water, and ammonia. Okay. Now these are what we call monodentate ligands. There are didentate and multidentate ligands, so we'll have a quick look at some of these as well. But on your syllabus, really, the main focus is on the monodentate ligands. So I've got some of these here. You can see the unidentate or monodentate, what I call them. And you can see, you know, a common feature of them. They don't have to have a charge. These are charged species. They've got negative charge. You've got your chloride ion, your hydroxide ion, and looks like your cyanide ion here. This would be carbon. This is your nitrogen with a triple bond. And these are obviously charged species. And here we've got water with its lone pair. Sorry, water with its lone pair here. And you've got your ammonium here, ammonia with its lone pair here. Bidentate or didentate refers to the fact that the molecule can form two dative bonds, and you can see here some examples of this. So you've got the ethane dioate, C2O42 minus. This is this molecule here, and you've also got this species here, okay, diamine. So you've got the two lone pairs. So this is why these ligands can actually form two dative bonds to the central atom. Okay, so we say this is a multidentate. This is called EDTA. And you can see here there are four lone pairs that can be, these are the lone pairs that actually form the dative bonds. Okay, so you've got 1, 2, 3, 4. So this is a multidentate. So like I say, really your syllabus focuses in on the monodentate or unidentate, which is where they only form one dative bond per molecule. And you end up with two particular shapes. There's another shape in complexes called square planar, but we don't look at that at WJC. But you should recognise these two shapes here, hopefully from your topic on VSCPR, which I will be doing for year 12, I think, in the coming weeks. So if you want to go back and look at VSCPR, always useful. So that will be coming up in the future. Look on the calendar. So you'll recognise these two shapes. This shape here is, well, octahedral, and this shape here is your tetrahedral. And you should also know your bond angles. So your octahedral, hopefully you know, is 90, and your tetrahedral is 109.5. Okay, so these are the two shapes you need to be able to draw. I highly recommend, just having a little practice and not assuming you can draw it. So we'll look now then at the actual complexes or complex ions that you need to know for your syllabus. There's lots of transition metal ions, lots of complex ions, but you need to just check your syllabus, make sure that you know which ions you need to know the colour and shape of. So if we have a quick look, okay, this is obviously our octahedral shape. It's 90-degree bond angle. And what I've done here for you is I've just got an image. Again, this has come directly off the blended learning. And you can see here, you've got your complexes. You've got the iron 2 and the iron 3. We've got some chromium complexes, some cobalt, and some copper complexes. And we're gonna talk about these complexes in a number of ways. We're going to discuss their colour, and we're also going to talk about something called ligand exchange. But like I say, you're going to have to, and this is the bit of transition metals I don't like, the bit of chemistry I don't like, is learning the formulas and learning the colours, and it's just rote learning. You're going to have to do it. Okay, so well, that's not a great image there. I've cut that off. I've just got a couple of species here, some different complex ions. You can see that one's not very good. There should be an OH2. I've kind of managed to cut that off there for you, but you know, it'll be there, like it is there. So these are the kind of shapes. You just need to be able to draw the octahedral shape, and then, you know, for example, if it was cobalt, H2O6, it's basically this species here, but you'd have a cobalt in the middle. If it was the, I'm just trying to think, the chromium, hexaqua, you'd have this one here, it's a chromium, and instead you'd have the chromium in the middle. So it's not particularly difficult to draw. This molecule here, you know, I've got my kind of square planar, I've got my ammonias clustered around the copper here, and I've got an OH2 and OH2 here with a charge, which is a 2+ charge. And as I say, you do need to know their colours, which is a bit of a pain, but you know, you're doing chemistry, so you're just going to have to learn them. Okay, so those are the octahedral complexes. You've also got your tetrahedral. There is only 2 that you need to know. This is going to help when you come on to do your ligand exchange. So you've got this cobalt and this copper. So there's your shape. Again, like I say, practice drawing it because you may be asked to draw them. All right, good. So, like I say, learn your colours, learn your formulas of the complexes. These are the only ones you need to know, and you've got your tetrahedral ones as well. So I'm going to talk to you now about copper sulfate. So copper sulfate is blue, so that's the kind of solution that you'd expect when you dissolve copper sulfate in water. And when you dissolve copper sulfate in water, you would expect to form this species here. So the waters would surround the copper. Fantastic, I don't have a problem with that. Okay, we're going to look at ligand exchange. So we're going to take some copper chloride. Okay, we're going to take some copper chloride and we dissolve that in water. And it's blue. And you might think, yeah, well, it's copper, copper's blue. But if you know your colour of your complexes, you'll see that actually copper chloride should form a yellow-green solution. So why has it formed a blue one? We've got some copper chloride, we dissolved it in water, and we end up with a blue solution. Yet we know copper chloride should have a yellow-green solution. Well, let's have a look. This is what we call ligand exchange. If you think about your copper chloride, if you are adding it into water and dissolving it, you are going to have a huge amount of water molecules present. So you can see the green colour that we'd expect with copper chloride. However, due to the presence of lots and lots of water from dissolving it, equilibria, the Chatter's principle, pushes equilibrium in this direction, and we end up with a predominant of this transition metal complex. So you need to bear that in mind. You know, when you put these things in water, the first thing they do is they break apart, and then you get your ligands coming in. So if you've got lots of water, you're going to form this species over this species. However, we've dissolved it in water. Now what we're going to do is we're going to add a bit of concentrated hydrochloric acid. What do you think is going to happen, and why do you think that's going to happen? Let's have a little think about that. So hopefully, I'll give you a chance to pause the video there or to wait for the PowerPoint. Hopefully, you'll note it. You'll have said a green colour will start to predominate. So you can just see the copper chloride now has just been added. So it's sort of form this green colour we'd expect with copper chloride. So why does this happen? Well, obviously concentrating has to be concentrated. If it's dilute, you're just adding water as well, aren't you? But if you add a concentrate, you're adding lots of chloride ions into your solution, and then you'll start to push equilibria in this direction, and you'll start to form your green tetrachlorocuprate 2. Okay. So what about now if I add more water? Hopefully you'll appreciate that we could push equilibria back in this direction, and we go back to the blue species. So this is what we call ligand exchange, and it's all to do with, you know, relative concentrations of the ligands. Another one that's worth knowing, and this is why you do need to know your colours of these species and how to draw them. You know, you may be asked what would happen if chloride ions were added to this species. So you'd have to know, all right, okay, we're going to form the CuCl42 minus, and it's going to have a green colour, or yellow-green. Okay, another ligand exchange worth knowing would be with ammonia. So again, we've got our blue solution of either copper sulfate or copper chloride. It doesn't matter, we've dissolved it in water, and what we know is that we're going to form a blue solution because of the water, you know. Now, what happens when we add ammonia? When we add ammonia, initially what happens is we start to form this dark blue precipitate, and as we add an excess of ammonia, we get this royal blue, okay? And I'll just explain to you what's happening here. So this species, this was the one that wasn't shown very well on the previous slide. You can see now what it looks like properly. And you can see here, as we add the ammonia in, we're pushing equilibrium over to this species here, okay, which is going to be this royal blue. So we're just applying the Chatter's principle. Obviously, if I dilute this now and put lots more water in, then I'm going to push equilibrium back and we'll go back to our typical blue colour. Okay, so you can see why your species knowing their colours and recognising these complexes is so important. And like I say, to make your life easy, I've literally picked the ones off the syllabus that you need to know. There are lots more, believe me, a lot more. Again, what I've done for you here, there's another nice little video actually off YouTube, and it's looking at cobalt. And again, you can see this ligand exchange with the chloride ions. Obviously, to do this, you'd be adding in hydrochloric acid, probably conc hydrochloric acid, and we get this species form here, which is our blue one. And if you go back here, is it there? Well, maybe it isn't actually. But go online. If you follow this link, we'll take to YouTube, and you can watch a little video that goes through the process. It's quite nice to see it happening. So the next thing then, we're going to talk about why we have colour. All right. So obviously, colour is to do with the light passing through our solution. And what I've got here for you, you can obviously read this yourself in a moment. But what we've got here is we've got this spectrum of light. This is white light, and as you know, white light is made up of many wavelengths. And we've got here, you know, I've got my the species. We recognise the scandium. The scandium ion is colourless. Perhaps we'll have a think about why that is in a moment. Same with the copper plus, silver plus, and zinc 2 plus. This is why we don't really count as transition metals. One of the things about transition metals is they should form coloured complexes, okay, or coloured solutions. So, why do they have colour? Well, you don't need to know these orbitals. I always just put them up. If I'm talking about d orbitals, you should know your s-type, the spherical, and the p-type orbitals, the dumbbell. These are your d orbitals, and you can see there's 5 types of orbital. And what happens is, with our ligands, is if we look at our 3D orbital, at the moment here, we would describe these electrons as being degenerate, or these orbitals as being degenerate orbitals. And what that means is they're equal in energy. What your ligands do is when they come in and form their dative bonds, they actually cause these d orbitals to slightly, not massively, but slightly split in their energy. And you don't need to worry about this here, whether it's octahedral or tetrahedral and how it splits. For you just need to know the d orbital splits. They split in one of 2 ways. It doesn't matter which way. The point is it has split. And how much it splits depends on 2 things. It's the ion that you've got in the middle, so not just the species, but its charge. So is it Fe2 plus or Fe3 plus? And of course the ligands. This is why we're seeing different colours when we have ligand exchange taking place. We're changing that split. So why does that cause our solution to become coloured? Well, as the white light passes through, what will happen is we have some vacant higher energy orbitals here, and there's not a great deal amount of energy needed. So what will happen is your electrons, quantum levels, will absorb a particular wavelength of light. Remember, energy levels are quantized. It will absorb that energy and promote itself into a higher energy level. Okay. Now that energy actually corresponds to visible light. So you can see here, I've got white light going in. And if we look at the white light that passes through our solution, we can see that the wavelengths of light have been absorbed, and one of them, the ones that have been absorbed, I've marked here. So we've got green, yellow and red being absorbed, but blue isn't. And so when we look at our solution, it will appear blue. And you don't need to obviously worry about these wavelengths of light, you know, what particular wavelengths correspond to what particular colour. It's just getting the idea across. So, you know, for example, copper sulfate, we pass white light through it, you can see the red and the yellow have been absorbed, but the green and blue get transmitted. All right, they're not absorbed, and that's the colour we observe as it hits our eye. Now, on exam papers, you may see graphs that look like this. Obviously, they're not coloured, but we've got a solution of copper sulfate, and it's blue because we've just said the red and yellow wavelengths are absorbed. So, in terms of the you know, the kind of absorbance chart we get here, this is what we'd see. All right, so you can see absorbance, what colours are being absorbed. These aren't really being absorbed at all. But if we look at the red, we can see it really has been absorbed. So what wavelengths aren't being absorbed are your blue and your green, hence the colour. Okay, so I'm going to have a little pause now for you to do a little bit of thinking. Here's some nickel 2 sulfate, and this is the absorbance of it. Okay, and what I want you to do is just have a quick look at that and consider what the colour would be. What's being absorbed and what isn't being absorbed. Well, hopefully, let's give a little pause so you can have a think. Hopefully you see that the green's not being absorbed, so we'd expect this copper sulfate to be green. All right, so, you know, I have seen questions come up like this in the past, and it, you know, it shows you the absorbance chart, and you have to work out what the colour of the solution would be. It's the colour that's not being absorbed. Okay, and then this is, again, you know, I'm going to keep hitting back to it, because I do really think it's a very good resource. I have to say, I'm impressed with it. The blended learning. This is a question on the blended learning. It's given you, you know, an absorbance here. So it actually starts at 720, goes down and decreases, or you can go in this direction, it's increasing. So increasing in the anti-clockwise direction. So again, you know, it is on the blended learning. I'm just going to pause here just for a moment for you to be able to think about this question. So we've got a complex that's yellow in colour. What colour light will this complex absorb? So if it's looking yellow, it's not absorbing yellow. So what is it absorbing? And again, you've got this wavelength of 400 nanometers in the visible absorption spectrum. What colour is the complex? So it's got a peak at 400 nanometers. So it's absorbing the 400, which is here, purple. So I'd expect that perhaps to be yellow. Green, sorry, it's opposite. There's the 400. So it's absorbing the violet, so I'd expect the colour to be green. Okay, so yeah, typical questions. Again, you know, it's a bit of a pain. I'm sorry, you're just going to have to learn it. The exam board want you to know the actual colour that these ions form in solution. All right, so you're going to have to learn those. Just interestingly, the iron 3 plus is red-brown, and that's because you don't just get the iron 3 plus in there, you get other complexes forming that give their own characteristic colours. But you should know some of these. You know, you should definitely know, for example, the dichromate colour. This is the test for an alcohol or an aldehyde, which you might be doing in organic chemistry at the moment. You start with dichromate, which is orange, and it goes to chromium 3 plus, which is green. Okay, so that's one you should know anyway. Copper, you should know from GCSE, it's pale blue. Iron 3 plus, you should know from just everyday life, it's rust, that really brown colour. And the manganate, well, you've used manganate in your redox titrations, it's that intense purple colour. So, you know, it's not too much learning to do on what you already know. Just remember those little things, those little tips to remember what the colours are. So the next bit I'm going to talk to you about then is the reaction with hydroxide ions. So hopefully you know when you add hydroxide ions to these substances, they can form precipitates. And there is on the sessions we've done for year, well, I think it was year 10, it was year 11, GCSE. If you go back to GCSE chemistry, believe it or not, I have done a lesson on how to write ionic equations for precipitation. But we're just going to look at why these things form precipitates. And the reason is that these waters that are datively bonded to the ion, the charge is actually spread out over the whole molecule. So typically you won't put the 3+ on the ion here, you'd normally put it onto the bracket. So you'd have a bracket here with the 3+ outside the bracket. But the transition metal ion is pulling these electrons in this dative bond towards itself. And as a consequence, that's then pulling electrons from the oxygen's hydrogen towards the oxygen. All right. So what you end up with then is a positive charge, long, big positive dipole on these hydrogens, and that makes the species become acidic. So actually, I can't quite remember the pH of iron 3+ in solution. By the way, this iron 3+, this could be dissolving iron chloride in water, any iron 3+ substance in water. Remember, ligands will come in and form these dative bonds. So these hydrogens here are acidic, and they will react with things like hydroxide ions or anything that's a base. So what I've got here then is typically what would happen. So as we had increasing amount of hydroxide ions, what happens is these react with the H on here to form water. Right? So you take a H+ off from this water molecule. You can see now I've only got 5 waters, and now we've got a hydroxide ion on here. And in losing that H+ to form water, the charge becomes 2+. And then I can add more hydroxide ions. And if I add more hydroxide ions, you can see I've removed another hydrogen from water. So my waters are going down. And these waters, this isn't ligand exchange, by the way. These waters are becoming hydroxide ions by having their hydrogens moved off. And now we get a positive charge. Okay, so we've gone from 3+ to 2+ to plus. And this is the important bit. If I had another hydroxide ion, I could remove another hydrogen from the water. And the important thing is that now we don't have a charge. This is no longer ionic, right? There's no charge, and that means it can't dissolve. Remember, water likes to dissolve things by forming hydration spheres, attracting the positives to the dipole of the water. So now this is why we form our precipitate. And if you're acidic enough, if you know your metal's positively charged enough, you can actually remove further hydrogens. So if I add more hydroxide ions, this doesn't work for everyone, by the way, but your precipitate can then dissolve. So you can see now I remove another hydrogen and my water's gone down by another, my hydroxide's gone up by 1. And my charge, I've now formed a charge, and that's why it dissolves. And that brings me back to the copper. I'll let you need to worry about that too much, but this is copper, say chloride dissolved in water. I've added some ammonia, okay, and what happens is I've just added just enough ammonia to pull off 2 hydrogens from these waters, and that gets rid of my charge, which is why we form the precipitate. And then if I add more ammonia, I can start pulling off more hydrogens from these. In fact, you can see in total I removed 4 hydrogens. So I'll go back up to here. 1, 2, 3, 4 hydrogens have had their have been pulled off from that complex. And when you form charge, you start to dissolve again. So there we go. Just going back to there. That's what forms when you add a little bit of hydroxide. This is to get you to this point here where you've got no charge, okay, or this point here. See, I've added 2 hydroxide ions per mole, and then if I add excess hydroxide ions, we get the blue blue solution, deep royal blue solution form. So, in terms of the exam, how do you write this down? Well, the way you'd write that down is literally as a precipitation reaction. This again, I've got this straight off the blended learning. You can get quite complicated how you write these reactions down with hydroxide ions, but what I recommend you do is keep it simple. And you can just say, for example, this might be from iron sulfate. Okay, so I've got some iron sulfate, I've got Fe2+ ions, I've got sulfate ions, and because it's aqueous, lots and lots and lots of water. Okay, so you wouldn't form, you'd form, let's go back to see what species you'd form and go all the way back. Wait a second. Yeah, in water you would form this species, okay, with iron sulfate, FeH2O6 2+. And if I add my hydroxide ions in, I would add enough hydroxide ions to get rid of the positive charge, and we form this species. So, you know, writing these precipitation reactions is quite easy to do. You just need to look at the charge of the species that, you know, you're adding to the water, and then just add enough hydroxide ions to get rid of that charge, and then you've got your precipitates formed. And again, very, very sorry, you're going to have to learn these colours. Okay, so these transition metal ions, the colours of their solution, which you already had to know anyway, that was on one of our previous slides, but now you have to learn what happens when you add hydroxide ions, so the colours of the precipitates, and you need to know that the chromium precipitate, the Cr3+, actually will dissolve when you add excess hydroxide ions, and you should hopefully know why that is, so I've just added that there. Once you've formed your precipitate, which is this one here, the CrOH3 solid, I can remove subsequent ions from it, H pluses from it, and I end up with this species. So if I go back, look at this slide, basically with chromium you can get all the way down to here. All right, so you can form this species. And actually what we can say here is that the chromium is amphoteric in nature, which means it can react with hydroxide ions. Go back now to my chromium, so it can react with hydroxide ions. But equally, if I take that species, if I add in acid, it will absorb those protons, okay, and reform water. So this is why we describe something like chromium here, this chromium hydroxide, as being amphoteric. If we add hydroxide ions, we can go this direction. If we add H plus ions, we go back in this direction. We start reprotonating those OHs. Okay, so finishing off then, you know, catalytic properties. You do need to know how transition metals can be used as catalysts, and I would definitely recommend at least learning some of these. You know, so the transition metal and the process that it catalyzes. Don't just learn one, because they might say iron acts as a catalyst in a hard process. Name one other catalyst, okay, and the process. So I've definitely learned two. So why is it then that they act as catalysts? It's because of their variable oxidation states or their vacant d orbitals. Okay, so sorry guys, that one's not quite where it should be. Two types of catalysts, homogeneous and heterogeneous, and you need to know what that means. So hopefully you know homogeneous means your catalyst is in the same phase of the reactants, and your heterogeneous, it's in a different phase. And they you know, we explain the homogeneous transition metal catalysts. They work by having a variable oxidation state. So what they can do is they can oxidize or reduce one of your reagents to make it a bit more reactive, and then in the reaction they then become they get oxidized or reduced back to their initial oxidation state. So it's the fact they have variable oxidation states allows them to be these homogeneous catalysts. And heterogeneous catalysts, these are in different phases of reactants. And basically what happens here is your reactant acts as a ligand, and it bonds to your transition metal. And well, I've got a little slide here that shows you that. So it uses the vacant d orbitals of the catalyst, your transition metal, it bonds in, and it just orientates your molecules and brings them next to each other better in order to get a reaction to take place. So, you know, there's a lot there. Like I say, the difficult part of transition metals is learning your formulas and your complexes, and I would definitely look at your ligand exchanges. You know, it's quite commonly questioned. So we've got 1 minute left. I hope that's been helpful to you, yeah, good luck learning your colours. Write them down on a piece of card, put them in your pocket, and just look at them as often as you can. And that's it for this evening. So I'll say good night and good luck.